Hi, welcome to lesson 14D, the derivative function. The goal of today's lesson is to learn what a derivative function is and how to find it. So yesterday we were looking at rates of change of a few functions, and we noticed that when there were linear functions, that suppose we had some sort of linear function here, we noticed that when we drew the function, I think it was something like, it was 4x minus 8 or something like that, something along this line. I'm just going to draw a rough sketch here. So we had some sort of line like this, and then we wanted to find the rate of change at x equals 2. I believe that's the point that we're looking at. And we did the whole process of using the gradient y2 minus y1 over x2 minus x1, and we used f of x minus f of a, some specific point all over x minus a. So some point f of x and x, and f of a. So in this case it happened to be that x was 2, so we ended up doing, I forget what the function was, I think it was something like 4x minus 8 minus, when we did this was minus 20 or something like that, and then x minus 2. Was that what it was? I don't think so. 8 minus 8, that would give us 0, so that's probably not what it was. But anyways, it was, we had some sort of a function here, we had a certain point. The exact details aren't exactly necessary, but what we did find was that after this whole long process, we found that the gradient that we were looking for was 4. Okay, and I believe the function was something like y equals 4x minus 8, for example. So we found that that was 4, and then we realized when we found the actual equation of the tangent line a few minutes later, we saw that the equation of the tangent line was 4x minus 8, which was exactly the same as the function we were looking at, this line. Now I didn't give the graph yesterday, but what we can see is that the gradient of the line, or the tangent line, happened to be the same as the gradient of the line itself. And that's because if you were to draw a tangent to a line, that tangent would actually lie completely on the line, okay, because the tangent to a line wouldn't touch the line only in one place. So we could do the same thing with any other sort of line. If we found some other sort of line, again, if we're looking at, even some sort of negative line, suppose that's something like y equals negative 1/3 x plus 2, for example, just as a rough estimate. If we were to go through the same process again, no matter where we use, whatever point we used as our a, f of a, anywhere along there, because that's a constant line, we would see that the gradient at any one of those points would be negative 1/3. So we need to be aware that the tangent, or the slope of the tangent, the gradient of the tangent to any point on the line, is still just going to be the gradient of the line itself. Okay, so that's fine and dandy. And it's going to be constant all the way along. What's going to be a little bit trickier is when we look at equations of curves, and suppose we have some sort of a curve, and normally these curves are always drawn in the positive quadrant, so this time I'll draw it in the negative. So that's some sort of curved function, and we'll see that if we were to draw a tangent line to this function, there's the point of tangency right there. We see that the tangent line has a negative gradient. If we go down here, there's another tangent line where the point of tangency is right there. that tangent has a gradient that's less steep than this one. If we go a little bit over to the left, to this point of tangency right here, we'll see that there's a point of tangency. We'll see that this tangent line to that curve is more steep than even the first one. So we can see that around a curve, the gradients of different tangent lines at different positions along the curve will have different values. Okay, so what we're finding actually is, what we're going to be finding is the gradient function. Okay, so the gradient function or derivative function is the same sort of thing, because the derivative function is the same as the gradient at specific points along the curve. And if we have some function f of x, then the derivative function itself, or the gradient function, is going to be f prime of x. That's called f prime of x. And if you have f prime of a, suppose x equals a, so the point of tangency would be a here, then f prime of a, so the gradient function evaluated at that point of a, the x value of a, is going to be the gradient of the tangent at the point where x equals a. Okay, so let's take a look at a little example along here. So I've prepared this function, and this function is f of x is 1/3 x minus 2 all squared minus 1. So if we're to find, we can find specific values. So if I say, let's find f of 1, so here's x, or sorry, f of negative 1. So here's x equals negative 1 right here. And if I find f of negative 1, I'm going to substitute negative 1 in for x, and then I can find this 1/3. Negative 1 minus 2 is negative 3. Negative 3 all squared is 9. Minus 1, a third of 9 is 3. Minus 1 is 2. So the point here, which we can clearly see from the graph, is negative 1, 2. If I draw a tangent line at x equals negative 1, I'll put this here, and then I will draw the tangent line. So that's the point of tangency. At this moment, we can't find the gradient of the point of tangency, or the gradient of the tangent line at that point, because we need 2 points to find the average rate of change right now. Now that's the tangent line, so it only has one point of intersection. But what we can do is, because the tangent line is a line, we can set up the rate triangle of the line of tangency, and we can find the rate of change of the tangent line itself, and thus that would find the gradient not only of the tangent line at that point, but it also finds the gradient of the curve at that point. So I see here that this y step here, this rise, is a change of negative 2, and this run, this x step, is a change of 1. So therefore the gradient of the tangent line at that point is going to be negative 2 over 1, which is just negative 2. And that's also the gradient of the curve at that point, because the tangent line at the point of tangency will have the same gradient as the curve at that point of tangency. So what I'm going to do here is I'm also going to plot this point. I'm going to take this point of, I'm going to graph the gradient function down below, and so at x equals negative 1, which is right here, we see that the gradient of the tangent is negative 2. So if I graph the gradient function down below at x equals negative 1, I'm going to plot a point, here's negative 1, a point at negative 2, because now this is the gradient function that we're looking at. So this is not y, or this is basically y prime, or f prime of x. Okay, and it's of course still along the x-axis. Okay, so that's one point. We can then find, I'll do two more, I'll do them just as simple as this one. This time I'm going to find the gradient right here at the vertex of this quadratic. So I draw the tangent line here, that's a horizontal tangent, and we see that if we were to find the gradient, well, here the gradient, there's no rise, so the rise is 0, and the run can be as long as you want, so I'll just say for fun it was 4. So obviously the gradient at that point is going to be 0. Therefore, so the gradient of the tangent at that point is 0, which shows me that the gradient of the curve, this parabola, is 0 at that point as well. So if I change this, take this gradient at x equals 2, and I plot that point down on the gradient function down here, we see that that's 0 at x equals 2. And then what I'll do is I'll come over here and then go to x equals 3, and I will again plot draw the tangent line here at the curve. So this is the point of tangency right here at x equals 3. Again, I'll draw my rate triangle. I missed the spot that I was looking for exactly there, but draw the rate triangle here. We see the rise, or the y step, is 2, and the run, the x step, is 1. So for that point of tangency, the gradient again is rise over run, which is delta y over delta x, which is 2. So again, when x equals 3, the gradient of the tangent line is 2, which then tells me that the gradient of the curve at x equals 3 is also 2. So I plot this point now, x equals 3, and gradient of 2. And, nope, wait, is that correct? No, it's not correct, sorry. Please forgive me. That wasn't x equals 3, it was x equals 5. There we go, x equals 5, and the derivative, or the gradient of 2. So I have calculated 3 gradients around this curve, and at each point of tangency, the gradient of each tangent has been calculated, which ends up being the gradient of the curve at that point in each of those spots. And then if I were to notice the pattern and line these up, I can see that the gradient function for this parabola, this quadratic function, the gradient function is actually linear. Notice that where the gradient is 0, the gradient of the original function is 0, that's exactly where the gradient function crosses the x-axis, at 0. The sign of the gradient over here to the right of the vertex is positive, that's positive 2. We see that down here to the right of this x-intercept, the graph of the gradient function is above the x-axis, meaning it's positive, and where the tangent to the curve is negative, over here, we see that the gradient function is below the x-axis, which means that the gradient function is negative at that point. Okay, so what we're going to be doing is we're going to be looking at a few more of these tomorrow in class. By looking at the rates of change of tangent functions at points of tangency along curves of a variety of functions. So what I'm going to do is I'm going to leave you with a couple questions to look at. Please take a look at example 4 on page 354 and ask the self-tutor by clicking the button to explain things to you, and then peruse through questions number 1 to 3 on page 354 before coming into class tomorrow. We'll look at a couple examples and we'll go through the investigation together, and then after that you'll have a chance to work through those questions. So, thanks for watching, and we'll see you in class.